This video is about deduction, which we're going to encounter as derivations and proofs in the logic of propositions. Let's start with a simple example. Suppose that you knew that if Descartes was a dualist, he believed the mind was separable from the body. And suppose you also knew that Descartes was a dualist. You could infer that, of course, Descartes believed that the mind was separable from the body. We could symbolize this argument very easily. If Descartes was a dualist, then he believed the mind was separable from the body. Descartes was a dualist, therefore he believed the mind was separable from the body. And we could recognize it as an example of a more general pattern, which for historical reasons is called modus ponens. Now, we know that we can test this argument for validity using a truth tree or using a truth table to show that there is never a time when the premises are true and the conclusion is false, and that's what makes it valid. But if we wanted to emphasize that the conclusion S is a logical consequence of the premises, we might do it by writing it out like this. I would first start by numbering my lines. I want to write the premise D arrow S and the premise S. And then I would want to say that I have inferred, the premise D, the second one should be the premise D. And then I would want to say that I inferred the sentence S from lines 1 and 2. So I could write it like this, and then I would add a little bit more notation here. I'm going to add one more thing here. This particular set of lines, which are called scope lines, that track the scope of our assumptions. We'll be clear about what those mean a little bit later on. But for now, what you can see here is a display that shows your reader that you have inferred or derived the sentence S from the sentences on lines 1 and 2. And we could even add more notation by telling our reader what pattern of reasoning we used to derive S from lines 1 and 2. So if we use the convention of calling this pattern of reasoning modus ponens, we might write MP here, call it modus ponens by using the acronym MP, and then we could put MP here. And that would fully explain to our reader that we inferred the sentence S from lines 1 and 2 using the pattern called modus ponens, where the D is playing the role of the script P and the S is playing the role of the script Q. And this is now your first example of a derivation. And again, we could add a little bit more notation to tell our reader that these are assumptions. And indeed, that would be a perfectly fine way to display our reasoning. Now, as it turns out, we're not going to use this kind of notation. We're going to use slightly different notation, but we are going to use line numbers and scope lines and use a justification column always to explain to our reader what justifies this line appearing on this list. And that has everything to do with what a derivation is. So a derivation is an ordered list of sentences where each sentence on the list is either an assumption or it is a sentence that is inferred from other sentences on the list using an inference rule. And an inference rule is just going to be a small pattern of reasoning that we antecedently know is valid. So let's look at another example to try to emphasize how a system of derivations that uses inference rules can be thought of as a system that codifies chain arguments. And I'll show you what I mean by that. So let's look at this example. Suppose we have M arrow E and neg D, and then we have M and H. And I want to conclude from that therefore neg D or neg G. I could check to see if this is a valid argument using a truth tree, and indeed it would turn out to be valid. But if I wanted to explain to someone how I reasoned my way from the premises to the conclusion, I might do it by taking the following steps. I might say something like this. Well, first, let's start by assuming that M and H is true. Now, if the premise M and H is true, I can infer from that therefore M has to be true. And what I'm doing there is just using a very simple argument pattern that says that if I ever have a conjunction, I can always infer one of its conjuncts, and that's a valid argument pattern. Now, why would I want to infer that M is true? Well, because then, if I assume that the first premise is true, and I now have derived that M is true, I can infer from both of those that E and neg D is true. And what I've done now here is just used the modus ponens argument pattern. P arrow Q, P therefore Q. And so in each little argument here, I'm using the premises in the original argument to derive something. And sometimes I use something I have previously derived, right? This is what's called a chain argument, because in the first argument, I have inferred M as a conclusion. And now this M becomes a premise in this next little argument. So now I've derived E and neg D. And then I could say, to explain my reasoning, well, look, if E and neg D is true, then I can infer from that neg D is true. And here I'm using the same argument pattern as before. It looks a little different because I'm inferring the right conjunct instead of the left conjunct, but that's also going to be a valid argument pattern. And then I could finally say, well, look, if neg D is true, then it has to be the case that neg D or neg G is true. And what I'm using there is a slightly different argument pattern that says if P is true, then I can always infer P or neg Q. And in this way, I can display my reasoning from the premises here to the conclusion using a chain argument, where at each step of the way, I'm using one of the premises of the original argument to derive a conclusion that then can become a premise in a future argument. Okay, so now this is a very kind of long-handed way of writing what I'm doing, and I would have to display all these patterns here every time I used one. And so instead of writing this all out in this way, I'm now going to rewrite it as a derivation. So as a derivation, what I do is I write my premises, and I label them as assumptions because I'm going to assume that these are true. And I use just a script letter A to designate them as assumptions. If those two premises are true, what can I infer from that? And that's not as open-ended a question as it sounds like, and you'll see why shortly. But when I say what can I infer from that, I mean using a set of argument patterns that we agree to confine ourselves to using that we're going to call inference rules. So let me first write out what we've done here in our chain argument as a derivation. The first thing I did is I concluded M, and I concluded M from line 2. Then what I did is my next conclusion here was E and neg D. And that was something that I inferred by using the first premise, which is labeled as line 1, and then whatever line number is where the sentence M appears. So it's line 1 and 3. So I'm going to put 1, comma 3, because that's where that came from. Then my next conclusion on line 5 was neg D, and that came from line 4. And finally, my last conclusion was neg D or neg G, which came from line 5. And we're very close to now having a complete derivation. The only thing that's missing is some notation. And here's why. So far, if I was reading this chain of reasoning and trying to reproduce how someone reasoned their way from the premises to the conclusion, I could see that this person believes that M is a conclusion that I can derive by using only line 2 as a premise. But I don't know what reasoning pattern they're using because they haven't told me. You and I know that what we used was this pattern of reasoning, and all we need is to give it a name. If we gave it a name, we could call it maybe rule 1. Suppose we called this pattern here rule 1. Then I could write my justification by writing that line 3 came from line 2 by rule 1. And then I could, for instance, maybe call the next one rule 2, and I could justify the next line by saying that it came from this line E and neg D was the logical consequence of lines 1 and 3 using rule 2, and so on. And I could just label them with numbers, but that's not a very useful way to label things because it's hard to remember which numbers match which rules. And so the system that we are going to develop doesn't use numbers for the rules. And in fact, it takes advantage of the symmetries and redundancies of our language to label the inference rules. So our inference rules are going to be labeled like this. First, I'm going to tell you what the labels are, and then I'll show you why those are called that. The first pattern here that says P and Q, therefore P, this one we're going to call and elimination. The second pattern that says if P then Q, P therefore Q, we're going to call arrow elimination. The third one is just another example of and elimination. And the fourth one here, this pattern here, we're going to call or introduction. So our system is going to be a system that uses a pair of inference rules for every logical connective. Every logical connective is going to have an introduction rule and an elimination rule. So there's going to be 10 rules in total plus 1. When we use this language of elimination and introduction, we have to be very careful because it's somewhat metaphorical. So it's motivated by wanting us to think about derivations as if they're purely syntactic, that all we're doing is manipulating symbols, but it can be a little bit misleading. So in the first example of and elimination, when we say that we're eliminating an and, what we really mean is that the conclusion is a sentence that doesn't have the symbol wedge in it, that was inferred from a sentence that did have the symbol wedge in it. And in that sense, we have eliminated the and. But notice the difference with the second example here. With arrow elimination, the sentence that we derived, Q, is a sentence that doesn't have an arrow in it, and it was derived from a sentence that does have an arrow, but also a second other sentence. This is a two-premise rule of inference. So just be really careful with this. Arrow elimination requires two premises. You must have the statement that is the conditional and the antecedent. Then you can infer the consequent. So if we use these labels here for our justifications, then our complete derivation looks like this. Line 3 was obtained from line 2 by and elimination. Line 4 came from 1 and 3 by arrow elimination. Line 5 came from 4 by and elimination. And line 6 came from 5 by or introduction. And this is now your example of your very first complete derivation.